Here we're going to talk about electric fields and electric field lines. All masses generate or create gravitational fields, and all charges generate or create electric fields. Masses are affected by the gravitational fields of other masses, but they are not affected by their own. Similarly, charges are affected by the electric fields of other charges, but they are not affected by the electric field that they create. We need to be very careful here, as it's going to say here in just a minute. When we talk about charges and electric fields, we need to be clear, are we talking about the field that our charge creates, or are we talking about the forces that our charge is feeling due to the fields of other charges? If we had just one charge with all other charges at a distance of infinity, this single charge would experience a force of 0. It would create its own electric field around it, but it would not be in the presence of anybody else's electric field, and therefore it wouldn't feel any force. So, as I just mentioned here a minute ago, we need to be very careful if we're talking about the electric field generated by this charge, or are we talking about the effect on this charge by the electric field generated by some other external charge distribution? By convention, electric field lines point away from positive charges and toward negative charges. At each point in space, electric field lines show the direction of the electric force that a tiny, by convention positive and often imaginary, test charge would feel at that location. Visually, the number of electric field lines that are directed away from a positive charge or toward a negative charge gives us an idea about the magnitude of the charges creating the field. And we hope to show you that here in a little bit. Let's draw some electric field lines around a positive charge and then around a negative charge. Electric field lines go away from positive charges. I'm going to draw that. And these lines are actually in 3 dimensions, aren't they? They're also coming out kind of towards us and they're going away. But on a 2-dimensional piece of paper, it's difficult to show that. But this is not a 2-dimensional electric field, it's 3-dimensional. Similarly, electric field lines end or terminate on negative charges. And so we need to make our arrows pointing toward a negative charge like that. And by showing the number of field lines on the left being equal to the number of field lines on the right, I've deliberately drawn 8 in each case. That is an indication that the magnitude of this positive charge is equal to the magnitude of that negative charge. In any drawing where 2 charges are in there together, the number of field lines should give you some indication of the magnitude of the charge. These point charges, all point charges, create non-uniform electric fields. And what that means is the electric field is stronger in some places and weaker in other places. And wherever the field lines are close together, which is close to the charge, you can see here where my pen is, there's a short distance between the field lines here. That means that the field is strong. Out here, the field lines are much further apart, you see. So that means that the field is weaker. This is a non-uniform electric field. What about between the plates of a charged capacitor? I've made these capacitor plates especially big so we can kind of draw in what's happening. The top plate is connected to the positive battery terminal, right? Which you might have learned. The long line is a positive battery terminal. The short line is the negative battery terminal. When this is charged, the top plate will acquire a net positive charge and the bottom plate will acquire a net negative charge equal in magnitude to the positive of the top. So we want to draw the same number of pluses as minuses. The field lines go away from positive charges and towards negative charges. I'm trying to draw those evenly spaced. There is actually some what we call fringing that happens out here. I won't draw all of them in. I'll just draw a couple. There is a little bit of that going on the edges, but in large measure, we're not worried about that. We're only worried about what's going on here within the body of the capacitor. And therefore, capacitors exhibit uniform electric fields. The strength of the field is equal at any point. And you can see that the field lines being equally spaced represents that. All right, there is an easy equation. We'll run into this a lot later that relates the difference in voltage between the capacitor plates to the strength of the electric field that exists between there. Perhaps I should do that on here. Should I put a little electric field vector? There you go. Multiplied by the distance between the plates. We'll run into that equation at a later time. Let's draw a couple of pictures here. Charges that are equal should have an equal number of field lines, kind of like that. And of course, this is also in 3 dimensions, and there are an infinite number of these because they're just imaginary. You can see here I've drawn 6 field lines leaving the positive charge, and I've drawn 6 field lines terminating on the negative charge. What about when we have 2 positive charges? Field lines originate on positive charges and they terminate on negative charges. So basically, we don't have any lines that terminate in this picture. They all run away, something like that, perhaps. And again, because the charge magnitudes are equal, I've shown an equal number of lines in each case. These electric field lines, they never tangle, they never cross each other. Let's finish with this one. This one has twice as much positive charge as this one has negative charge. So for every one that lands on the Q1, we're going to end up with some that don't. Something kind of like that, where you can see here 1, 2, 3, 4, 5 charges are terminating on the negative charge. How many are originating on the positive charge? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's perfect right there.